All right, I think we are live. Okay, today is February 14th, new day, new challenge. Before we start, kind of have to go back to yesterday. Yesterday was a really bad experience. I mean, I was stuck on the problem. It's actually just a medium question, and I was actually I had this question 2 years ago. All right, I think it's June 2019, and then it took me like a long time. We're talking about 4 or 5 hours to get a comfortable and satisfactory result. And yesterday, the same thing. It took like 2.5 hours just to get to the level that I feel comfortable with. The problem is very simple, in retrospect, right? It's just to find the shortest path in a matrix with some cells are open where you can go, and some cells are obstacles and you cannot go. And it's a straightforward breadth first search, and then done. That's basically the end of it. But for whatever reason, when I saw this question, I'm not sure what I was thinking back 2 years ago. But yesterday, when I saw it, the first thing in my mind is dynamic programming. Dynamic programming. Just kind of got stuck in dynamic programming, and we did eventually pass the online judge using dynamic program, but the runtime is horrific. We're clocking like 5,900 or more milliseconds, while using the breadth first search, we can get it around 700 milliseconds. So it's a gigantic difference. Now, the good part is yesterday when I was just looking through the discussions, and then I did spend time to look at the A-star search. I think that was something I didn't do back 2 years ago. I was just too fed up with these questions. I didn't do. But yesterday I did. I did look into the A-star search. Now the code provided by that post was very well engineered, or over engineered, should we say. It kind of makes things a bit more complicated than they're supposed to be. But basically, reading that post, it gave me a refresh on what A-star search is. I mean, that's a good part of doing all these problems. All these algorithms you've heard of, you probably have seen it and learned it in a class, but you never really implemented it yourself or used it. But now you see how it can be implemented in a real problem. Now, A-star search is basically a breadth first search, BFS, on steroid. That's the end of it, right? BFS on steroid, and the steroid itself is heuristics and a priority queue, and that's it. Basically, in BFS, what we do is we do not discriminate on all the children nodes. We just push all the children nodes that have not been seen before into the queue, and then we just keep pushing and keep popping. That's the end of it. There's no thought process on which child to visit first. Now, A-star search is the same as breadth first search. However, it uses heuristics, which means based on the position of the node, we can have a general idea how costly it is to reach the destination from every node. Just in general, a ballpark estimation, because we know. And yesterday's question, if the node is close to the destination, then the heuristic cost from moving from that node to the destination is smaller compared to a node that's far away, right? So there is a certain way to estimate these heuristics that can be consistent. Well, this is important. The heuristics has to be consistent across all the nodes. And the question yesterday does have this, heuristics. Basically, just imagine you have a grid, you have a matrix without any obstacles. Then you can compute the shortest distance from any node to the destination. And this computation is straightforward, which is just the maximum value of your x and y position, your coordinates. And that's it. So that is the heuristics, which is consistent among all the nodes. And then when you try to decide which child to go to, you use a priority queue, and then you calculate a weight for each node. And the weight of the node is the heuristics plus the number of steps that has to be taken before reaching this node. So basically, the heuristics is the actual distance, actual steps you have to take to reach the child node, and the predicted, consistent, heuristically steps you will take to reach the destination. So you add them together, and that becomes the overall cost of choosing that node. So when you decide to visit a node, you're gonna search your priority queue, right? And then you will always pick the one that's on the top of the priority queue, which has the smallest cost. So every time you're picking the smallest cost, and by doing this, it can significantly reduce the search space. So you don't have to, in a BFS, you have to search the entire matrix. But with A star, you will skip a lot of the cells because they have bad heuristics, so they are lower on the priority queue. So you will always pick the good ones, and when the good ones already arrive at the destination, and that means you already find the best option. So you don't have to worry about the nodes that are low on the priority queue that you will never ever encounter. So this is good. This is very good to go through this and kind of understand. Oh no, A star is nothing fancy. It has a fancy name, but is basically it's just BFS with heuristics and priority queue as a steroid. Now this goes back to previously we had encountered a situation where we have to implement the Dijkstra algorithm, which is, it's complicated if you haven't done it by hand by yourself. But now you think of it, it's similar. You have a priority queue, and you have the current weight, which is just the distance it takes to reach a certain node, and then you push all the nodes into the priority queue, and when you want to visit the next one, you pop out the one with the smallest cost. So they all follow the similar pattern. And then, is it possible for me, say, to write the Dijkstra right now without any reference? Probably not. Probably I need to go Google and refresh my idea. But by going through all these questions, right, it gives you more chance to see these things occur, and then it has a better you have a better understanding of when and how to use it. So that's basically the value of going through all this. Anyway, let's go to today's first check on this. I don't think there's anything that we need to worry about right here. Somebody commented on this. I don't even know what I commented on. Anyway, let's do this. Ooh, bipartite. I have taken a graph class before, and we used a library. What library do we use to handle graphs? Oh man, Python library for graphs. What is it called? I don't think they're actually searching the ones I'm looking for. Oh my dear Lord, I forgot the library to handle graphs. No, it's not plotting. It's not plotting. It's graph. It's a something I can search to bring out this library. What can we say? Is that like graph similarity? Something like that? Graph, no. Okay, is this the one that we can take a look? Is that iGraph? Oh yes, that's the one. iGraph. Yeah, that is the graph thing that we used. Yeah, it was very powerful, very powerful. And the tutorial, I remember when I took the class, the tutorial was it took a long time. Yeah, I think it's the same thing. Right? It took the same thing, iGraph, and it can give you good plots and drawing graph and the layout. Yes, I remember this. Anyway, so when I was taking the class, we have to determine like whether a graph is bipartite, and it's basically just a command, a function call. You have a graph, you load it into iGraph, and then you call this function, and then it tells you whether it is bipartite or not. Anyway, let's look into it. I kind of forgot what is a bipartite. Undirected graph with unnodes. Okay, each node is numbered. Okay, you are given a 2D graph where graph U is an array of nodes that U is adjacent to. Okay, so it's like a dictionary representation of the graph. It's got adjacent. It's not adjacency matrix, but adjacency list. Yeah, this is called adjacency list. It's adjacency. Okay, more formally, each V in graph U, there is an indirect edge between node U and node V. Yes, the graph has following property. There are no self edges. Okay, so there's no loops, no like this. No parallel edges. So it does not contain. So there's only one edge between two nodes. If V is in graph U, then U is in graph V. That's true because it's undirected. A graph may not be connected, meaning there might be two nodes that cannot reach each other. Yes. A graph is bipartite if the nodes can be partitioned into two independent sets, such that every edge in the graph connects a node in set A and a node in set B. It's basically just a graph. You try to implement the bipartite function. What's the definition again? Into two independent sets, A and B, such that every edge in a graph connects a node in set A and a node in set B. Alright, let's see. What does one mean? There is no way to partition the nodes into two independent sets, such that every edge connects a node in one and a node in the other. Hold on. What is? This is true, right? We can partition the nodes into two sets. So 0, 2, and a 1, 3. So what? So the nodes can be into two independent sets. So this is, we'll say, A and this is B, such that every edge in the graph connects a node in set A and set B. Oh, okay. So we have 4 edges, and then if we say 1, 3 is a set, 0, 2 is another set, now we can see every edge is connecting the two sets. So if we can find two sets that can satisfy this, we say this graph's bipartite. Actually, let's see a more official, I guess, bipartite explanation on this. Bipartite. Now this one is a better explanation. Bipartite graph. Let's take a look. A bipartite graph, a bigraph, is a graph whose vertices can be divided into two disjoint and independent sets, such that every edge connects a vertex in U and to V. Okay? Complete bipart. Oh, so that's like a dense layer in a neural network. It's a dense layer means it's a bipartite graph. That makes perfect sense. Okay, so we are clear on the definition. Now we're trying to solve it. So the first thing, these don't really matter that much. The first thing in my mind, when you're talking about this disjoint union, right? What's in our mind? Union find. So maybe we can do this unit find. But again, unit find is one of those algorithms that I've heard of it, I've used it, and never been able to write it myself out of just by hand. So probably have to go through some online resources to find union find. But let's see if we can use this union find idea to solve this problem. So union find means we just find a node, and we find another node and try to union with the node. So eventually we'll be able to find a but union find will get everything under one because they're all connected, right? The 2 is connected to, say like we start with 0, right? Well, 1, okay, that's one union. 2 is a union. 3 is union, so they all belong to the same union. I don't think that works. This one's the same. Everybody's connected to everybody else. So that's not going to work. Okay, so union find probably is not going to work. All right, so let's try something else. So what we want is to find 2 sets of nodes that the edges connecting to all of them, which means we go through the edges. All right, goes through the edges. The edge has 2 nodes, and then another edge has 2 nodes, right? So say for example, for here, we go through this edge, so it connects to 0 and 1, right? They say all the edges, such that every edge connects a node in set A and set B. So we know 0 must belong to set. We assume that a graph is bipartite. So we say 0 must be in, say, set A, 1 is in set B. Now we go to the next edge, and then the edge, ideally, if we can find some edge that has a connection to one of the nodes that's already in the set, so we go for the 1 connected to 1. So we know 2 must be in set A, and then that's it. So 1 is done. Now we look at 0, so 3 must be in set B, and then last one we just kind of check. Okay, that seemed to be working. I'll go back to this one. Why is this not working? Again, we go from 0. So from 0 we have 0, 1, 2, 3. So we know 1, 2, 3 must belong to one set. 0 is another set. And then we find out that 1 and 2. So 2 is supposed to be in the 0 in the set A, but now it's in set B. So that's why this one is not a bipartite, which means I think this might work. So in terms of coding, so what we here have is the node. Okay, we have the node. We know the node 0 connected to 1, 2, 3. So we can create 2 sets. All right, done. And then we go to node 1. And I probably shouldn't go to node 1. We probably should look into this, because if we go to a node that has not been considered before, then we run the risk of having, we don't have a connection, right? So we're always trying to have connections. And if there's a, say, disjoint, say there is a node that cannot be reached, like the graph is not connected, and that's definitely a false, right? That definitely is a false, because you have to have, well, is that a false? Let's say that all the nodes can, yeah, it should be, all the nodes should be reachable. So if it's disconnected, it's not going to work. So we do the first, and then we're going to search inside, say for this, search in this, and then we pull out, search for this, pull out, search for this, pull out, and then we go to, so how do we structure it? Should we be like, so like a 0, we do all of them, and then from 0 we go to its child, right? We go to 1. So 0 go to 1, and now we are starting from 1, and then from 1 we can find its target, and then it has a 0, and then we know 0 and 1 must be different. So do we need to have a so like all of these are numbers, right? So the numbers, okay, they're all numbers. So we can create just a list, and then once we decide, we just put the letters in it. So 0 would be A, and then 1, 2, 3 will be B, and then we from 0 we'll go to 1. So basically, just traverse through the entire list. Yeah, we just traverse through and then see if everything holds. If everything holds, then we're good. So 0, we visit it, we go to 1, right? We go to 1, we see 0, and it works. And then from 1, we go to from 1, we check 0, 2, and if they all work, and what do we do if they all work? And we go to the 0. Yeah, we go to 0, and then we see like 0 is visited, and we go to 2, right? And then 2, yeah, it's just like we visit every single node, and then that should be it. Okay, it's like a the DFS, right? The DFS, we can write it in recursion, so it'll be should be simpler in terms of the coding part. Let's take a look. Open it up. Hopefully this one will result in something more meaningful than what we did yesterday. Yesterday was really bad. Okay, so what we're gonna do is we are going to say we're gonna have a groups. I'm gonna call that a. Oh, how do you know the size? It says graph.length. I don't even know a graph.length. We don't know. We have to like compute it to know the length of the graph. So I think it'll be easier just do it this way, right? And then we can also say, well, let's make it a default dict, right? We can from collections import default dict. We can make it such that we can make it, and let's just say str, right? So it's empty string. It will return an empty string. I'm not 100% sure, so we're gonna double check. I think this will give us empty string. Import default dict a equals default dict. Let's say str. A 0 should be an empty string. Yes, that's good. So we're gonna empty string will be the marker to say if a node has been visited or not. So now we're gonna say DFS. We're gonna give us an index. That's our current node. It's gonna be an int. Do we return anything? Do we return anything? Yeah, we can return. We can return the bool if it's true or not. So what I'm gonna do is I'm gonna start from a node, right? Then we're gonna start from the node. That's the index, and I'm gonna check. What we're gonna do is we're gonna put the start. So we're gonna say if groups index is if not group index, which means I have not visited it. Well, it's definitely, we have decided that we will not visit the one that has been visited, so this one is actually not necessary. So we know the index has not been visited before. However, no, because we already, so we do have to, okay, we do have to have a one called visited, because when we add 0, we already set the group for these 3, right? But we haven't visited them, so we still have to visit them, so it's different. All right, so then we just make this a simple this, right? A simple this, and then we just say if. But we need to check, right? We need to check where I am, and we need to check where how do we know that all the nodes has been included in this? Because if we do like a run, right? We do a DFS run, and then we try to hit every node, but then some node is not included. Are we going in order, right? We're going in order. Yeah, from 0 to n-1. Yeah, we're going in order, but they don't give us the n, so we don't know the n, but we are in order. So eventually we have to also check. Okay, so that's something we have to worry about later on. So now all we know is if we have not a so when we start and and then we assign some other nodes, and we want to visit, and then if it has, so how do we know where I stand right now? Or to say if I visit a node and that node has not been labeled before. Now the node will be labeled. Let's just label it, right? Let's just label it. Let's just label, because we're gonna go 0 first. It's always so. Let's just label 0, right? Let's just label 0. Let's just say 0 will be labeled as 1, right? That's our label. And when we go, we're gonna go 0 first. So that means it's already been labeled. So everything will be labeled. So what we're going to do is we're going to check the child. So for child in graph index, and I'm going to say if child not in groups, then groups child will equal groups index times -1. That means it's the opposite group. Else, if child is already in the groups, so we know the child's group, then we need to see if the child's group, if the child group has to be the same, has to be different from the parent. Else, I'm going to say elif groups child is the same as groups index. This means that we have the index, which is the parent. Actually, we don't use index. It's confusing. Let's use parent, right? So we should say the parent should be of a different group as the child. But if the two is the same, so we can just return false. And then we do all of these things, and after we're done, what we're going to do is so first we are going to visit it. So we're going to say visited equals a set, right? So we're going to say visited dot add parent. So we visited this, and then after we labeled all of them, then we're going to go again for child in graph parent. I'm going to visit each child, and I'll say if child is not in visited, then we DFS child. And once everything is done and then it's good, we are going to return true. So we're going to run DFS. I'm going to say if not DFS, we're going to start from parent 0, we're going to return false. However, if it is true, that just means the connected part is true. So we also need to see whether there's any missing. But in order to do that, we need to know the total number. So we still need to know the total number. So we probably need to just go through and then, just bite the bullet and then kind of see how many nodes there are. How do you compute the total number of nodes? You don't know. Well, we know the largest number. We can go just through and then we find the largest number. That's fine. That's fine. Let's do that. Let's find the largest number, and so we know. And if we find it, then we don't even need to use a dictionary. We can just use a regular thing. So let's say n equals 0, and then we just be for children in graph. Oh, are we going to include every single one? Is the length graph.length? Oh, it's a graph.length. Ah, come on, man. It's just the length graph. Yeah, so we don't have to do this. We just do 0 times n, and then we're gonna set groups 0 equals 1 because that's how we want. And we can say the child in this and groups child equals groups parent times this. It's good. Also, if they're the same, then we have a problem. Is that correct? If child not in groups, no, it's gonna be if groups child. If not groups child, that means the child has not been assigned yet. So if not groups child, the child equals this. Else group child has checked already. I want to see if it is equal to the parent. If it is equal to the parent, then we are going to return false. And then we're going to go through the parent and go through the children and see if it's not, we're going to visit it, right? And then we're going to do this. So that's that. And finally, what we're going to do is we're going to do a product of groups. Is there a Python thing that can do product? So I'm going to say Python product of a list. I don't even need to accumulate it, just a product. Do they have a product? Reduce. I don't want to use reduce, but I think it's NumPy. Well, they have NumPy, but I don't want to use it. All right, that's it. All right, let's buy the bullet. That's probably have to do reduce. Okay, let's do reduce. Nah, let's just feel like it's. Let's just do this. I'm gonna say for G in groups. Actually, we can say we're gonna return all G for G in groups. Right, for G in groups, and then the G has to be not equal to 0. All of them, right? So if there's any 0, that means we have a unconnected graph, and if the graph is not connected, then it cannot be a bipartite. So run the 2. We have 2 simple test cases, and then just to see if any of them give us trouble. If they do not, I want to run some custom test cases. Basically, just to check, to check on the unconnected part of the solution, which I definitely think is likely. And also there are other tests to run, other edge cases to run. So we have a graph here, and we need to change the function name. It's called isBipartite. Run it. Ooh, we failed the first one. Why is that? Why do we fail the first one? Answer is false. Our return is true. Okay, so we have a child, and the child. Why would that be? All right, we need to take a look. So for child in this, if group's child equals to group's parent, and then we return false. Oh, because I didn't do it here. I'll say if not in visited, and I say if not, we're gonna return false. Yep, that should do. Yep. Actually, I think we can send a not DFS child, and then we return false. We can put them in the same. Yep, both pass, and let's run some test cases. So one test case we can run is based on this. So what we're trying to do is let's create a graph with some. Let's just say we take 2 out. So basically, let's take 0 out. If we take 0 out, oh, they're all connected. So if we take 2 out, so 0 doesn't change. 1 we have to remove 2. So 1 we have to remove 2, and 2 we have to remove the entire thing, and 3 we have to remove 2 as well. So basically this is this. So this should give us false, even if 1, 3. Huh. It is true. What the? So if we have a if it's a disconnected graph, and we still say in the graph, so it's not required that it's not connected. Yeah, this is not connected. 2 is not connected, and we want to have this, and we can do this, which means we just return. If we just return DFS 0, right, and then this one shall pass. Okay, so that's what it is. Like, disconnect will not cause problem. I don't know. I mean, this probably is in graph theory. The bipartite means as long as you have 1, as long as it's possible to find a bipartite within the graph. Doesn't really matter if the graph is connected or not. Let's try just a single, right? Just a single. It's always a good test case. Let's see if, say we have only a single one, right? It's a single node. It's, oh, my bad, 0. So we have 0. Oh, but we cannot, because 0 cannot connect to itself. How do you represent a node with only 1? Oh, I know. This is just a single node. It should be false. It's true. How is it true if it's a single node? You can't even divide. There's only a single node. You can't even divide it into 2 parts. Oh, we say 2 set. One set contains 0. The other set is an empty set. And then there's not even edges between them. Anyway, let's try this. Let's try. I've actually tried it. 0, 1, 3. We tried it already. Any other thing that we can try? We think about like complete. How about this? 3 independent node with no edges. That's still true. Huh. Interesting. We're gonna submit it, but I am not quite sure about the. Oh man, don't be like this. We have to go through the whole thing again. Ay, 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 ay. Why is this one wrong? Okay, that's. Wow, we're not in a good streak. Oh, we're past the majority of the test case, so probably just a little bit of work this can be done. All right. Oh my goodness. Output true. Expected false. Okay, so what are you saying? All right, let's write it out. It's only like 9 nodes. 0 is by itself. Mind ya, 0 is by itself. And 1 connecting to 2, 4, 6. 2 connects to 1, 4, 8, 9. Okay, 8, 9. 3 connect to 7, 8. 7, 8. 1, 2, 3, 4 connects to 1, 2, 9, 8. Okay, 4 is done. 5 connects to 6, 9. 5 connects to 6, 9. 6 connects to 1, 5. 7, oh man. 7, 8, 9. Oh man, they're all connected. And 7 connects to 3, 6, and 9. 7 also connects to 9. 8 connects to 2, 3, 4, 6, 9. And 9 connects to... 9 also connects to 2. Oh, I think I got it wrong. 1, 4, 8. Oh, I forgot a 9. Holy moly. Two, 4, 5. 2, 4, 5, 6, 7, and 8. Okay, so 0 is the odd one out. And then expected to be false. Better we get it to true. Okay, I'm not sure. So expected is false. Ah, please don't do this to me again. 2 days in a row, I'm gonna go crazy. I'm gonna lose it. Yeah. Okay, that's fine. That's fine. Let's do this. Instead of return it, we're gonna call DFS 0, and we're gonna just print visited and then print groups. Just, you know, sanity check. Oh! 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 Oh, ah! I never thought about this. Okay, so, we have to start from every single one. We have to start from every single one because of this thing happened. So we need to return all of them has to be true. All right. Does all of them has to be true? Yeah, I think so. If any of them is false, then we have it. I think it's all of them. So we say all DFS I for I in range n. Isn't that what we want? And then it shouldn't cost too much because, well, it's still, what the heck? The groups visited, all of them visited, but the groups, oh, you didn't assign it. Ah, okay. All right. Let's do this. For I in range n, we will have to visit every single node. So this becomes, yeah. So for I in range n, right? And then we say if not groups I that has not been signed, then we always sign it to 1. So we sign it groups I equals 1. Then we do DFS I. And we say if not DFS I, then we return false. And then eventually we return true. Okay, let's try this one. I mean, the idea is if we have to go through every node, treat every node as the beginning of the graph to avoid this type of situation where you have disjoint from the start. And we just go through it, and if this node has not been visited before, then we just assign it a value, which is to say, if you have not been visited before, which means you are disjointed, and then we just assign you as 1. And that pass, let's hope it passed all the rest. I'll pass, okay, so this is our new condition for return. And we are going to, let's actually just copy and paste the entire thing, because I make some, yeah, this is not needed. Groups, visited is this, good. I'll pass, and we're going to do this again. Okay, so we do this again, and we run this test cases. This test case I don't have. All right, let's try it again. Yes, got it. A little bit setback, not too bad. Okay. There are better solutions. This is our solution. I mean, it's ON, right? Definitely ON, because we run 180 and these are like 175, so it's basically the same. It's ON. The reason it's ON is because that we have visited. So every time if it's visited, we're not going to go the DFS. Right? It's not in visited. I suspect if you do BFS on this, it will be faster, because you don't have the overhead of setting up the recursion. But we are not going to go that way because this is simpler. Well, it's actually the same. You probably have to write a BFS as well. You know what? Let me write this, and then we try the BFS. It shall be the same way. Almost exactly the same. We just change the DFS into BFS, and that's it. Because this is to visit every single one that's connected to the graph right now. Okay, so DFS solution. We assign each node either 1 or -1. And as we traverse through the graph, we check whether a parent node and its child have the same signs. If they do, then the graph cannot be a bipartite. We do this until we visit all the nodes. The one trick is to start DFS at all nodes, because the graph can be disconnected. I think it's called dis, not disconnected. So it's still going to be ON, and we run at 180 milliseconds, which is 47% ranking. And before we go for the check, let's run actually I can copy and paste the entire thing. I think the only thing different between a BFS and a DFS is the BFS version is this part. So instead of calling this, we can call it the BFS, right? When we have a parent as well, and we have a visitor as well, is everything's the same, and we just need a queue. Let's also use deck, because I think deck is a better one for this. I'm gonna say deck queue equals deck when we put parent in it, and then it's gonna be while queue, and say node equals queue.pop left. After we pop, I'm going to say for basically the exact same thing. I'm going to say for child in graph node. If not, and then it's going to be node. If we're going to return false. And then for child in graph node. We might be able to combine these two. Oh my goodness, what are you doing, man? You're changing the wrong thing. Holy moly. This is ridiculous. You're changing the wrong thing. Oh man. This is terrible. Yeah, because this one we have to wait until all of them are labeled before we start visiting them. But here we can push into the queue right after they have been visited. So if not, and then if not this, and blah blah blah, and then I just say if child not in visited, and we can do queue dot append child. Right, so it'd be like this until we done, and if we're done, we're gonna return true, and then we're gonna do this. Sorry, and do this and not BFS. Return this, and then so solution 2. Oh, what the heck? We have trouble. Why do we have trouble? Like we hit a endless. Oh, because the visitor is not here. Visited should be when we trying to push. Yes, here. At child, and we are going to be for I range. If not I, we're gonna say in group I was 1. That's cool. And then if I not in visited dot add I, and then we're going to say, I like this. Yep. I'm pretty sure this one will be faster than the other one. This one, BFS to solution, and we run this test case just to make sure everything is check. Run it, and then we pass. We see the runtime. Improve a little bit. BFS version, same thing. ON, we hit 176 milliseconds with 63% ranking. These basically are the same. Right? There's no big change in this. Lines. Okay. All right. Now we're done with this. We check on this. Anything special? I don't think anything special is happening here. Is there a solution? There's no solution. We are going to the problem itself. We can actually search is graph bipartite. Is graph bipartite? It's a medium question. It's about right. We solved it, so we're gonna like it. And check on discussion. See Java clean DFS bipartite valid color. Maybe this can also check each individual. Yes, that's true. For a term, first color. Valid color. Why is it so much easier? So much simpler. I'll do int color. So colors 0 and valid color. Colors from I. 0 haven't been colored before. Blue and red. Go is trying to use two color to color graph. There are any adjacent nodes. I have the same color exactly. Initialize color for each node. Okay. If it hasn't been colored, use a color to color it. That's what we did here. If it doesn't color, we color it. And then use the other color to color all adjacent nodes. Okay. If it has been colored, check if the current color is the same as the color that is going to be used to color it. Check the current node is the same as the color that is going to be used to color it. Okay, so this is fine. So it's like it's not visited, so we don't need to use a set. It's not visited, and valid color is going to be. I'm going to color it with 1. If it hasn't been colored, I'm going to color it with 1. I'm going to color this with I. Then colors is this and graph, and then I'm going to say if colors of node is not 0, and then we're going to say colors node equals color. So if the current color is the same as the one I want to color it, then we'll return true, which means that it is valid, because I want to color it as 1, and if it is not 1, then it's going to be bad. And then color node equals color, and then for the next one, and we're just going to check. Graph color minus color, yes, I'm going to color it with a different color, and if it's the same, that's good. If it's not, that's bad. Oh, that's good. Very good. Very good. Very good solution. I don't know what that means. Oh, it's a Chinese dude. Alright, I'm going to upvote this and then just read one more. Yeah, so this one, I think in my case, I was checking as well. Why do you still use the set? I mean, it seems like we don't need to use the set. Right? We just... Okay, if not, that means the child has not been colored and then we are coloring it. And then we're trying to visit the child. What are you afraid of when you say it is going to be 0? Okay, what I was afraid of, I don't even think I was afraid of anything. 0 is not colored, right? 0 is not colored. So if anyone is not colored, then we just going to say it's going to be 1. And then we don't need this. Yeah, let's update. Let's update. Let's get rid of visited. It's not necessary, right? When you come in, when the parent come in, parent has a color. So for the child's color, so I say if child has no color, we're gonna color it as the parent's opposite. If the child has color, then if it's the same as the parent, we return false. And after check all these, we're going to see if we need to go further. For this, if let me say if not groups child, which means the child has not been colored before, and it's false, then we return false, or return true. So in here is the same. If has not, then if has not been colored, we color it, and then we can do this. If not, df is high, which means if it gives me wrong, and I return. So let's go back to this one. Ooh, that's not correct. If not, then we try it. And then we try DFS I. I mean, I didn't change anything. I just used the group's child to determine whether the child has been visited before. Why is this not right? Say if not groups I, which means if it has not been visited, I've set it to this, and then which means what do we like not do it? And then this will be true. Oh, which means even if you're saying that even if this thing has been because we change, we say not groups. Oh yeah, that's why. Because yeah, because I say if it has not been visited, then I say if it has been labeled, then I don't visit it again. If it has been labeled, then I don't visit it again. But then here we're gonna visit every single node. This might be faster because we reduce the number of visits here. Let's give it a shot. See if it's any faster. But these are like a micro upgrade. It's not going to make any difference. I think it's going to make any difference. And it gave us a wrong answer. What the heck? I think it's because some just not visited. Yeah, we probably have to visit every single one. Alright, so it's a wrong idea. I think the way we set up, that means, but we do visit every node, but then it doesn't visit its, I think it's because like this one just doesn't visit all the nodes if we do it this way. I'm trying to figure out. It's supposed to be true, but I return false. Yeah, and then we are going just to check return false. Let's print groups time. Oh, goodness, what are you doing? Did you ruin this? Probably not. Let's print this. What is a false? I split into two. So what was the problem? I have 0 connected to 1. 1 to 0, 1 to 3. 0, 1, 0, 1, 2 to 3. 3 and 3 to 1, 2. So it's like this. It shall be false because, oh, it shall be true. Expected true. Yeah, 0, 3, and 1, 2. Actually, no. 0 to 1, 1 to 0, 3, 2 to 3, 3 to 1, 2. And my result is 0, 2, 3 is together. Ah, that's what I say is false. All right, let's see. Now, so we set 0 and set 1. Yeah, and then if not, so we DFS 1, so a child. So this gets -1. Okay, so for child, and it's just this one. If not, groups child. Groups child is already, so we don't visit it. And then return true. So the first one will return true. And next, we're gonna go here. And start from here. And then it's child. 0, which is good. It's not equal. Good. And then we have 3. So 3 becomes 1. 3 becomes 1. And then we don't go to any one of them. And then we go to 2. And a 2 do not have, yeah, we have to visit every single one. So we have to visit every one. We cannot just stop here. That's because we're supposed to keep going, but we didn't visit everyone. What's the end if we do it the other way? All right, let's go back to our old one and just copy and paste. This is our old solution, which we use visited to determine whether a node has been visited before, which works. And we don't need these two parts. This works. And I was just trying to see the idea of, yeah, let's go. Let's not change this. I think this way of thinking, right? We add a node, we change the color of the children, and then we try to see which children we need to go to. So this is this idea. The solution, the suggested one, is slightly different, right? Slightly different. So what it says is, so it's also DFS, right? What it says is I currently have my node, right? And then I have a color I want to assign to the node. And if the assigned if the assigned and the and then we're gonna just call it colors, and we can say n equals len graph colors is going to be 0 times n, right? And then we're gonna say if colors node, right? That means the node has been colored before. We're going to return colors node equal to color, because I want to assign this the color, and my current color already assigned. If they are the same, then we're good. Elsewise, well, have not been colored before, right? If this node has not been colored before, then colors node, because we want to color it with color, and after color it, we need to go to all of its children, and then when we go to the children, we can check whether the children has been colored. If the children has been colored before, so that means we have visited the child, and then we can return see if it's a good color or not. So I'm going to say for child in graph node, right? And then we're going to say graph node, say if DFS child. So we're going to do minus color, true. If it's not true, then we're going to return false. And then eventually we're going to return true. And then we're going to return, we'll have to go every single node. So for node in range n, for everyone, we're going to do if colors node, if not colors node, then we're going to say DFS node color, we're going to do 1. And if it's already colored, then we don't do it, because this already goes to every single one. The only one is not. So we say if not and not, we're going to return false. Otherwise, we're going to return true. Okay, let's see solution 3. I only have one open. Let's have all of these open. Okay, I pass. So this is the official, more or less the official solution. It's shorter, and we can submit it. I think this one will work. No, this one works. It's more of like an official solution. Let's see. Eventually, yeah, it's the same solution. Let's also check Lee 215. Oh my goodness. Didn't even say anything. Oh. Anyway, so I'm going to write one more comment here. This is from, I want to cite the person that I copied it from. So this is from here. I feel it is more concise DFS than my version, and it's also clearer what the algorithm is trying to do. We assign colors to all the nodes. What we want to see is that all adjacent nodes can be colored by all the adjacent nodes are different colors, have different colors. If not, then the graph cannot be bipartite. We start from color any node that has not been colored before, and then we go to all of its children and want to color them with a different color. As we visit the child, we compare the child's current color with the desired color. If the child does not have a color yet, we assign the desired color to it. Otherwise, we compare. Otherwise, we compare the child's current color with the desired color. If the two match, we end the search and return true. Otherwise, false, which means a bipartite cannot exist, cannot be found. We also need a trick to visit each node, to treat each node as root, just to handle the case of disconnected graph. ON, we run at 172 milliseconds, I remember. And this one, 172, 78%. Okay, good. That's it. 3 solutions, pretty good. I'll leave right here. We had a better performance than yesterday. Still a little bit hiccup throughout the way, but overall we did it. All right, let's end it right here, and I'll see you guys tomorrow for tomorrow's challenge.